Okay, so we're ready to actually look at some aspects of our solar system. Let's take some inventory of what's in the solar system. Well, first of all, we've got the sun, and in fact 99% of the matter of the solar system is in the sun. The sun is by far the most massive object in our solar system. We have the 8 planets. There used to be 9 planets, but in the last couple of years Pluto was demoted from planetary status, and so at the moment we have 8 planets. We have several dwarf planets now, including Pluto, and when Pluto was demoted from planetary status, several other objects in the solar system were promoted to dwarf planet status, including, as we'll see, Ceres, the largest asteroid. We have over 120 moons in the solar system, and in fact, once we've kind of done this inventory and looked at the planets, we'll see that many of the more interesting objects in the solar system are actually the moons. There's a lot that's going on there. Thousands of asteroids, not all of them have been cataloged, and so there's a lot going out there, moving around there that we don't know of. And countless meteoroids and comets. Comets are constantly being pushed inward to the inner solar system, and so that's what we see, but there's many more comet remnants existing out there just at the outskirts of our solar system. Well, in the structure of the solar system, the sun is at the center of the solar system, as we said, with most of the mass. The interior or terrestrial planets are the 4 planets: Mercury, Venus, Earth, and Mars. So-called terrestrial because Earth being the terre, these are the Earth-like planets, and so they are the terrestrial planets. The asteroid belt lies between the orbits of Mars and Jupiter, separates the terrestrial planets from, as we'll see, the Jovian planets. The asteroid belt, this actually was a $500,000 question on Who Wants to Be a Millionaire, was where is the asteroid belt, and it actually lies between Mars and Jupiter. The exterior Jovian planets, the 4 planets, Jovian planets, are Jupiter, Saturn, Uranus, and Neptune. Pluto is now a dwarf planet, or oftentimes categorized as a KBO, which stands for Kuiper Belt object. In fact, just beyond Pluto is the Kuiper Belt, which has a lot of these icy structures out there, and the belt itself extends the solar system to approximately 80 astronomical units. Here's a pretty picture of looking at the night sky at timed exposure. And in this picture you can see many of the solar system objects. You can see stars and maybe a planet. You can see galaxies. But unfortunately, in this time exposure, something has come along and scratched our time exposure along here and put these lines in here. And that something is an asteroid. An asteroid is much closer to us, so on a time exposure it's actually moving, in this particular case moving in a transverse direction, and so it moves across our timed exposure and we see that streak of light. Otherwise it might not have been detected. So an asteroid would have a definite signature if we were trying to take a prolonged or timed exposure of the sky, and this is one way that you might discover a near asteroid. Here's a a comparison of the Sun and the planets, size comparison, so you can see the relative size between the terrestrial planets and the Jovian planets, how much larger the Jovian planets are compared to the 4 terrestrial planets. And indeed, the Sun, the curvature of the Sun is shown as well, so we can see how much larger the Sun is compared to the 8 planets. We also have Pluto included on this, which is just a artifact of the fact that this diagram was made before Pluto was demoted. So we have to go ahead and knock Pluto off here. Here's another such diagram, again just showing the curvature of the Sun. You can see how much bigger the Sun is compared to the planets and how much larger the 4 Jovian planets are compared to the 4 terrestrial planets. And again, we have to get rid of this little dot here that designates Pluto. Yet another comparison. These are always neat little diagrams. The 4 terrestrial planets here and the 4 Jovian planets here. Well, if we were to focus in on the terrestrial planets, the 4 planets within the asteroid belt, as we said before, they are called terrestrial because they resemble Earth in composition. Earth is the tear, and so the terrestrial-like planets, the tear-like planets, the terrestrial planets, are like Earth in composition. In particular, if we look at Earth, we have some characteristics. We have a crust, we have a mantle, and we have a core. Earth actually has 2 cores, an inner core and an outer core, which is consisting of molten-like matter. And at one time, the other terrestrial planets were probably the same. Mars has a mantle-like structure with a core. And whether that core is molten at this time is unknown, but certainly it was molten in the past because there's much evidence of volcanic activity on Mars in the past. Mercury has a much larger inner core, accounting for its greater magnetic field and its greater possibility of its density, given that it's got very light mantle material. And the Moon probably had a core at one time as well. The reason that these are similar is the process of differentiation. As these bodies cool, the heavier material, which is the iron and the metal-like material, tended to coagulate near the middle of these cooling processes, and the lighter material was pushed out. So what we mean by differentiation is that it's denser near the middle and lighter towards the outer radius of these objects. So we have iron-rich cores and rocky silicate exteriors, which are less dense. Here's a comparison of the Jovian planets to Earth. You can see how much smaller Earth is compared to Jupiter, Saturn, Uranus, and Neptune. And the reason we call these 4 large planets the Jovian planets is because, in particular, they're also jovial. I mean, I've never ever seen a Jovian planet with a frown on its face. So definitely they're just jovial planets. Another reason we might call them Jovian is because they actually resemble Jupiter in composition. So Jupiter being Jove, if it resembles Jupiter, it's Jovian. So being like Jupiter, the Jovian planets have some similarities. In Jupiter, we have some metallic hydrogen and molecular hydrogen in its interior. Hydrogen is indeed a metal. We often don't see it that way because in our experience it's a gas or it's part of a compound, but pure hydrogen is a metal, And so in Jupiter we have a lot of this metallic hydrogen close to being solidified, and that actually accounts, as we'll see, for its very large magnetic field to have this metal material swirling around. Saturn has molecular hydrogen and metallic hydrogen as well, and so does Uranus and Neptune, but Uranus and Neptune may also have more of in their mantle a slushy water-like ammonia type mantle to it. Origin of the solar system. The age of the solar system is about 4.6 billion years old. How do we know this? We know this from the investigation of meteorites, which would be looking at pristine material from the origin of the solar system, because meteorites are just rocks that have been flowing around there for 4.5 billion years, and finally they hit Earth, and we get to look at something that was there at the beginning of the solar system. Earth rocks are somewhat aged to be younger because a lot of these rocks have already gone through processes that make them look younger or make them appear younger, which is the erosion and those kind of processes, or lunar rocks, which are aged to be older because there's less of these erosion processes on the moon. It's quite unlikely that the solar system resulted from random chaotic events, and more likely that the solar system was formed by a one-time event because of the circumstantial evidence that seems to point in this direction. What is that evidence? Any theory of origin we have for the solar system must somehow incorporate the following observations that we have on the solar system. One is, each planet seems to be by itself in space, seems to have cleared out an area so that it's by itself in space. Any theory of the origin of the solar system should try to take this into account. Also, the planetary orbits are almost circular. Why are they circular, and why are they so well defined going around the sun? So they have low eccentricity. The orbits are in the same plane. Why is this? Why don't we have planetary orbits that are, say, going this way and that way and at this angle around the sun? Why are they more or less in the same plane going around the sun? Any theory of origin that we have for the solar system should try to explain this. The planets all orbit in a prograde direction. They all orbit in the same direction around the sun, which is counterclockwise as we look at it. Why? Most planets rotate prograde like the sun as well. In other words, the sun is rotating in the same direction that the planets are revolving around it, and the planets themselves are, most of them are rotating in that same direction, except for two of them. Venus slowly rotates retrograde, and Uranus is tipped over on its side and rotates almost perpendicular. But why do the 120 moons plus in the solar system also revolve prograde around their respective planets? Why? Any kind of theory of origin of the solar system might try to incorporate this as well. As we know, when we look at Saturn, with 32 moons, 31 of them are revolving prograde, counterclockwise around Saturn. There's one that goes the opposite direction. The terrestrial planets are different from the Jovian planets in terms of composition. Terrestrial planets are heavier materials, more dense, smaller, and the Jovian planets are large. They got hydrogen, the lightest material possible in them. Why? Any theory of origin we have probably should try to account for this as well. The asteroids have their own properties, and they have different compositions among them, but they're very old. So any theory we have for this theory of the origin should try to account for this. And comets are icy with independent orbits, originating far from the outskirts of the solar system, and then they have these very elliptical orbits. So we try to explain that as well. So here's one possible theory, the nebular theory. In this theory, we start with an idea that there was a cloud of gas and dust, what we call a solar nebula, of this cloud of gas and dust. It starts to pull in under its own gravity. So as it's collapsing under its own gravity, if there was any initial momentum at all, it'll become denser and hotter, and some of that energy, gravitational energy that is lost, it's being pulled in, is going to make it hotter and also make it start to rotate. So as it contracts, its rate of rotation increases because we start losing potential energy, gaining this kinetic energy of rotation. And as we'll see, if you take a cloud and you start rotating and you increase its rotation, the cloud will start to flatten into a disk. And so under this theory, the nebular theory, starting from this cloud that is being pulled in and rotating and flattening, we start forming what would be called the ecliptic plane. The sun would form at the center of this nebula, and the cooler outer regions of the solar nebula would then somehow form the planets and their moons, and they would retain this motion of rotation in the same direction and basically find themselves resulting in the same plane, the ecliptic plane. So the major motion of the solar system would be all in the same direction, revolving around the center sun, and the rotation would be the same, revolution would be the same result for the moons as well. So here we have this cloud of dust, starts pulling in on itself, it starts rotating. As it pulls in, it flattens out into a disk due to conservation of angular momentum, and we find ourselves in this ecliptic plane. It speeds up as it pulls in due to conservation of angular momentum, which in a very simple sense means that its velocity of rotation as it's going around multiplied by its radius is a constant. So as its radius gets smaller, the faster it moves. We're familiar with this when we see an ice skater. As they have their arms out, they have a greater moment of inertia. As they pull that in, their angular speed increases as their radius decreases. So this gives a pretty good explanation, at least for some of the general features that we see in the solar system. The fact that the planets are in a plane, that they all revolve around the sun in the same direction, that the sun rotates in that same direction, that the planets, most of them rotate in that same direction, that the moons around the planets revolve in that same direction. That all makes sense. However, modern calculations show that this swirling matter in this solar nebula alone would not be enough to form the planets, that it would just probably just continue to swirl. So as with any theory that might have a problem, you either have to, in science, you either have to throw it out or you have to modify it to include any problems that you might have. So a new theory is the condensation theory, which is basically the nebular theory with a little modification. In this condensation theory, dust grains act as condensation nuclei, so that as these dust collects and pulls in things to collect with it, we start getting this process called accretion, where matter starts pulling matter in, and small clumps of matter become bigger clumps of matter. So small clumps combine into bigger clumps called planetesimals and protoplanets. We kind of see this effect in everyday life in our atmosphere. When we have water vapor, it might be super saturated, and we have this high humidity, and there's no rain unless you have dust in the sky, and then that gives nuclei for the water vapor to condense onto, and as it does so, it forms water droplets, and then we get the result of rain. So this kind of idea of having condensation nuclei is very prominent in science, and a very valid theory. As the accretion process goes on, the surface area increases, and that just helps to speed up the process. Once we get these planetesimals and protoplanets, they may collide, and we'll get some fragmentation. This will destroy the smaller objects and result in increasing the size of larger objects as these clumps start to collect again. So gravity will help form the spherical sun and the 8 planets, not the 9 planets, but the 8 planets. And also would be left over would be dozens of moons and many asteroids and comets, these pieces left over from this beginning dust cloud. Also might be included in this is at some point the sun is going to fire into solar fusion, and when it does so, it's going to give off a lot more solar wind, and that might push away a lot of the smaller objects that might have existed in the solar system at that time. So here's a look at this solar system formation. We have this ecliptic plane, we have the solar nebula, and we have this collision, and things start to clump up, and at some point the sun fires up. After a few million years, we start getting the planets and the leftover debris, the asteroids and the comet debris, ultimately leading to what appears to be the solar system after a few 100 million years. It spins faster, flattens out, heats up. Accretion and gravity then form the planets. In this early solar system, it's going to be hotter near the center, especially where the gravity has been pulled in, and where the sun is eventually going to form. So the elements that cannot take the heat would be pushed out. And another way to look at that is the lighter elements under heat will have more kinetic energy, and hence they will move further away. They'll be harder to be held in check by objects that have weak gravity, like the terrestrial planets. So the terrestrial planets like Earth, Mars, Venus, and Mercury are trying to hold on to all the elements and compounds that they can, but the lighter elements like hydrogen and helium have a lot of kinetic energy, a lot of velocity associated with their kinetic energy, and hence they cannot be held to the Earth, and that's why the Earth does not have those kinds of elements in the atmosphere. Whereas as it gets cooler and further out away from the sun, these elements can be held in, especially by objects as massive as Jupiter and Saturn. So it's kind of a double effect there. With gravity and cooler temperatures, Jupiter retains those elements of helium and hydrogen, and hence it's a much larger planet with all the elements possible. So we call this differentiation and a differentiation effect throughout the solar system. So the terrestrial planets are composed mostly of rock and metal, heavier elements. They have high densities and solid surfaces. While the Jovian planets are composed mainly of gaseous type elements, have low densities, and no solid surface. They might have icy layers, but no real solid surface to speak of as you approach these Jovian planets. The masses and the radii of Jupiter, Saturn, Uranus, and Neptune are greater than those of Mercury, Venus, Earth, and Mars, and the densities of Mercury, Venus, Earth, and Mars are greater than the densities of Jupiter, Saturn, Uranus, and Neptune. So their masses are greater, but they have much greater volumes in proportion, so that their densities are much smaller than the terrestrial planets. Here's the way to compare some of these observations. If we take Earth as being a radius of 1, just for comparison, we're going to use Earth as our comparison planet, then Jupiter has more than 11 times that radius. So in terms of its equatorial extent, its radius, or if you look at twice that, its diameter, Jupiter is 11.2 times the Earth's radius. If we look at volumes, when you consider volume goes as the radius cubed, so the volume would go as 3 times that radius relationship. And so for Jupiter is 1,400 times the volume of the Earth. That means 1,400 Earths could fit inside the volume of Jupiter. 840 Earths would fit inside Saturn, 64 Earths would fit inside Uranus, and 58 inside Neptune. In terms of mass, taking Earth as being 1, Jupiter is 317 or about 318 times more massive than Earth. Saturn's about 95 times more massive. So not quite as the same extent of proportion in terms of mass, but still a lot bigger. The Jovian planets are a lot bigger than Earth in terms of mass. Density is the mass per volume, and you can see that when we take the mass per volume of the planets, the terrestrial planets are more dense. So they have more mass per volume for their whole extent. In fact, water by definition is 1,000 kilograms per cubic meter, at least pure water. So by definition, on this scale, water should be 1,000. Hence, Jupiter is just a little bit more dense than water, and Earth, being the most dense planet, is 5.5 times denser than water. Most of its density is in the core, where it could get up to 15 or 16 times more dense than water. We're very dense in the core, where we have iron and heavy metals. But on the average, 5.5 times more dense than water. Saturn is the only planet that's actually less dense than water. So if Saturn were a big beach ball, it would float on some huge ocean of water. The terrestrial planets are closer to the Sun. They're all within approximately 1.5 astronomical units, while the Jovian planets are far from the Sun. Jupiter is the closest Jovian planet at 5 astronomical units, and the other Jovian planets are far beyond that. Saturn's another 5 away from Jupiter, and then we go even further and further out after that. When we look at the orbits, Earth being 1 astronomical unit away from the Sun, Mars is about 1.5 astronomical units, Venus being about 70% of the Earth's orbit, and Mercury about 40%. but there's a big gap there between Mars and Jupiter. Of course, you have the asteroid belt in between, but Jupiter is at 5.2 astronomical units away, and so there's more than 3.5 astronomical units between the last terrestrial planet and the first Jovian planet. Here's a neat little law called the Toutatis-Bode law. It's an empirical law, which means it's just a law based on data. So it doesn't necessarily have any scientific or observational significance to it, except that it works mathematically. Take a look at this. Let's say you start with the numbers 0, 3, 6, 12, 24, 48, 96, doubling every time as you go, starting from 0, going to 3, and then doubling every time as you go up. Add 4 to each of these numbers, so you get 4, 7, 10, 16, 28, 52, 100. And then divide this by 10. So you get 0.4, 0.7, 1, 1.6, 2.8, 5.2, 10. This gives you the approximate astronomical unit distance from the Sun for the planets and the asteroid belt. Neat. Let's take a look at it. Here's the actual astronomical unit distance on the left here. And here's what we get from this simple Toutatis-Bode law, this empirical law. And we can see that Mercury is about 0.4 astronomical units away. Venus is about 0.7. Earth, of course, is 1. Mars about 1.5 or 1.5. Asteroids are about 2.8. Jupiter 5.2. Saturn around 10 astronomical units. Uranus around 20, and so forth. So it kind of works, kind of neat. So if you were walking down the street and you couldn't remember how far away Jupiter was or Saturn was from the Sun, you could possibly remember this Toutatis-Bode law and put it into effect. Well, we know from Kepler's third law that the time period it takes for a planet to go around the Sun is related to its distance from the Sun. The period squared is related to the distance from the Sun cubed, and so we can actually calculate or we can even measure the time it takes for the planets to go around the Sun. If we take Earth as being 1, in other words 1 Earth year, Mars is almost 2 Earth years to go around the Sun. So if we went around the Sun once, and the last time we saw it Mars was there, then Mars would have moved almost halfway around the Sun already again. Jupiter takes just about 12 Earth years to go around the Sun. So that means as we go around the Sun once, Jupiter moves about 1/12 in its orbit around the Sun, which means that if there was a prominent month in the previous year when Jupiter was visible, let's say for instance like this month would be October, if we saw Jupiter prominent in our month of October this year, next year we'll see it prominent in 1 month later, in November say, because Jupiter would have moved 1/12 of its orbit around the Sun. Hence we got to move another month, another 1/12 of our orbit in order to sync up with it. So every year Jupiter will be prominent in one more later month than it was the year before. Saturn takes about 30 years to go around the Sun, Uranus about 84, Neptune 164, Pluto 248. So Uranus will take approximately a lifetime to go around the Sun as we see it. So it almost always will be pretty much the same month every year, and definitely for Neptune, in your lifetime, if you see Neptune in a particular month, you got a good chance as you go around and get to that month again the next year, that will be the month to look for Neptune again. Here's an interesting thing that happened in April 2002. All 5 visible planets of the visible planets were in the sky at the same time. It's a good thing that alignment didn't just pull us out of our orbit from the sun. Now that wouldn't happen. Doomsday predictors who don't know science would always say something like that, but that's pretty silly. This kind of alignment where we have the 5 planets in the sky at the same time, 5 visible planets, happened again in March, April of 2004. It's kind of a rare occurrence, so we probably won't see that happen anytime real soon. Moons of the planets. Mercury and Venus have no moons. Earth has 1 moon. We call it the moon. We possibly have another moon. Some astronomers attribute this asteroid that has kind of gotten caught between a gravitational low between the Earth and the Sun. It's called Cruithne, and it takes about 4,000 years to make 1 orbit of the Earth. So technically, for some astronomers, they might call that a moon of the Earth. But for most astronomers, Earth really just has 1 moon, the moon. Mars has 2 moons, captured asteroids, real small, Phobos and Deimos, fear and panic, panic and fear. Pluto has 3 moons. Of course, Pluto is not a planet anymore. This is data collected in the last few years, this data on Pluto. Jupiter, Saturn, Uranus, and Neptune have many moons, at least 8 each. So that's another thing that would characterize the Jovian planets and distinguish them from the terrestrial planets, that the Jovian planets have many, many, many moons. Here's a comparison of the terrestrial planets with some of these moons. Here we have Earth. We have Venus, which is sometimes called the sister planet to Earth because it's almost the same size. We have Mars and Mercury. We have our moon, which is oftentimes compared to Mercury, at least in terms of its appearance, even though it's a lot smaller than the planet Mercury. We have the 4 Galilean moons, which are, in comparison, almost planet-like, because the 4 Galilean moons, 2 of them are on the size, about the size of Mercury. In fact, one of them, Ganymede, is larger than the planet Mercury. And the other 2 moons, Io and Europa, are about the size of our own moon. And Saturn has their largest moon. Saturn has its largest moon, which is Titan, and Titan is actually larger than the planet Mercury as well. So there are some moons out there which are planet-like and make them just as interesting in terms of looking at objects in our solar system. Here's another way to compare the terrestrial and Jovian planets, rotation and rings. The terrestrial planets rotate relatively slowly. They have no rings. They have few moons, Earth having 1, Mars having 2. And they have weak magnetic fields. We'll talk about this later, but having weak magnetic fields might be a manifestation of the fact that they actually do rotate slowly. Jovian planets rotate quickly. They all rotate less than an Earth day. Some of them rotate, 2 of them rotate on the order of about 10 hours, and the other 2 on the order of about 16 or 17 hours. All of them have rings. Now, we're quite familiar with the rings around Saturn, but all the Jovian planets have rings around their equators. All of them have at least 8 moons and strong magnetic fields due to their large size, the presence of metallic hydrogen, and their fast rotation rate. So they all have strong magnetic fields. Asteroids. We define asteroids as rocky objects with diameters ranging in size from about 100 meters up to about several hundred kilometers. So by definition, an asteroid has to be greater in diameter than 100 meters. If we go below that, we call them meteoroids. About 7,000 of the asteroids have been cataloged and have had their orbits determined, but there are thousands of asteroids out there, so there are many asteroids that have not been cataloged, and we may not know exactly what they're doing at any particular moment. Most of the asteroids are found in the asteroid belt between Mars and Jupiter. Or there might be what we might call asteroids or icy asteroids in the Kuiper belt beyond Neptune. Most of these might more accurately be called comets, but you could call them icy asteroids. The Galileo probe on its way to Jupiter photographed two asteroids, Gaspra in 1991 and Ida in 1993. As it made its way through the asteroid belt, it took it a few years and came up with these photographs. Here's a picture of Gaspra, and here's a picture of Ida and Dactyl. Ida is the asteroid, Dactyl is Ida's moon. So an asteroid can have a moon as well. Asteroid, it has the distinction of being the only asteroid and the first asteroid that has had a spacecraft land on it. The NEAR spacecraft, funded by the European Space Agency, landed on Eros in 2001. When it did, it took an elemental composition of the surface and found very interestingly that the surface was mainly composed of silicon dioxide. Silicon dioxide is the main component of rock. So they discovered that Eros was made of rock. Here's a picture of the largest asteroid in the asteroid belt, Ceres. This was taken by Hubble, and it's not a very good picture because, well, it's probably was not the main subject of this attempt to take a picture, and the Hubble is mostly used to look at more interesting things. But we can see that Ceres actually is rather spherical in shape, and it's about the size of Texas. So about the size of Texas, both in its length and width. Asteroids, almost all of them revolve around the sun in the same direction as the planets. So that kind of gives an idea that they were part of this original solar nebula and this flattening out of the solar disk, because they are retaining that same residual motion. Almost all are near the ecliptic plane, again supporting this theory that they are part of the original solar system. Many have highly eccentric orbits. And the size of about 1,000 of them have been determined. Most of them smaller, of course, than Ceres. About 20 asteroids have diameters of more than 200 kilometers. Ceres has a diameter of 940 kilometers, which would be about 600 miles. Large asteroids are spherical. This is a gravitational effect, so the larger you get, the more that the gravity tends to create a spherical object with more symmetry. But as you get smaller, gravity is less effective in this sense, and you get more irregularly shaped asteroids. Earth-crossing asteroids. Earth-crossing asteroids have highly eccentric orbits that somehow intersect Earth's orbit. And this could be a problem because if they intersect Earth's orbit at any point, Earth following that orbit, then there's some possibility that an Earth-crossing asteroid could collide with Earth at some point in the future. About 3 collisions occur in a 1 million year period. Most of these are small asteroids, definitely 1 kilometer diameter or less. A collision of a 1 kilometer diameter asteroid with Earth would have about the energy of 1,000,000 1 megaton nuclear bombs. So we don't want to have a collision with a 1 kilometer diameter asteroid anytime soon. Here's Asteroid Toutatis that had actually what we might call a close approach to Earth back in 2004, in September of 2004. Made a close approach to Earth on September 29, 2004. It came within 960,000 miles of Earth. Now Earth is 93 million miles from the Sun, so this is about 1/100th the distance from the Earth to the Sun. So in terms of the Earth to the Sun, it is 99% away from the Sun, 1% away from the Earth in that distance. But that was still 3 times the distance of the Moon from us, so still beyond the Moon by a factor of 3. Still too close to call, too close for comfort. Here are pictures of Asteroid Toutatis as it's rolling through the solar system. And because I have an active imagination, I'm looking at these pictures and it kind of reminds me of a crash dummy. If you're looking at it, it looks like a head and a body, and it crashes in, and hopefully if it ever decided to crash into us, we would have constructed a large airbag by then so we could soften the crash. It is the largest Earth-crossing asteroid known, 3 miles by 1.5 miles, traveling at 22,000 miles per hour, which gives it a lot of kinetic energy, and that's where its energy comes from if it were to collide with us, because it's most likely not traveling in the same direction as we are, so most of that kinetic energy would be transferred into the Earth as pure energy. It would deliver on 1 million tons of TNT energy. Here's a look at the Asteroid Toutatis. It kind of looks like a end-over-end flying football. And that's part of the problem, is to try to make a calculation of where it's going and what it's doing has to take into account the inertia among all the possible axes of this toppling football, and that's really hard to do. But the best calculations say that it won't come anywhere too close to hitting the Earth anytime in our lifetime. So that's a good thing. Of course, field goal kickers never intend to hit the uprights, and sometimes they do, even after their best calculations. They hit the uprights and it bounces back and doesn't go through. Here's a look at the sky, and we have a streak across this time exposure indicating a asteroid, and this particular asteroid is Icarus. If you remember from Greek mythology, Icarus was the son of Daedalus. Daedalus was the greatest inventor in the Greek times, in Greek mythology, and Icarus had asked his father, Daedalus, to make him some wings. So Daedalus did. He made him some wings, but he made them out of wax. And so he told his son, you know, these are great wings, you can fly around, but don't fly anywhere near the sun because your wings are made of wax. And Icarus didn't listen to his father, and he flew too high. He flew near the sun, and of course it melted the wings, and unfortunately Icarus fell to his death. So the moral of the story, I guess, is to listen to your parents. Here's a look at the inner solar system and the cataloged asteroids in this inner solar system. So we can see the Sun, Mercury, the path of Venus, Earth, and Mars, and this green area to the outskirts is the asteroid belt. Very interesting. So as we look at this, the red asteroids are the ones entering the inner solar system, and the blue asteroids, the blue marks, are the Earth-crossing asteroids. Here's the frequency of large impacts over a logarithmic time scale, or logarithmic energy scale, and logarithmic on time this way. We have a few impacts every million years or so. 65 million years ago, it's believed that we got hit by an asteroid that extinguished the dinosaurs. So that was a major impact 65 million years ago. There was a large impact about 100 years ago in 1908 in Tunguska in Siberia, and the effects of that can still be seen. So it was almost like a very large or multiple nuclear explosion, the kind of energy that came from that event. We'll talk about that in the next lecture. But that was several megatons of TNT equivalent energy in that explosion. Here's a look at the inner solar system and up to Jupiter. So you see the asteroid belt. And we see in the orbit of Jupiter there's also two other groups of asteroids equal ahead and behind of the orbit or of the planet Jupiter itself. And these asteroids are called the Trojan asteroids. They're kind of held in place by a lull in the gravitational attraction between the Sun and Jupiter. Jupiter and the Sun having more or less the same gravitational attraction on these asteroids, and have kind of trapped them in this lull of the orbit of Jupiter. So 50 major asteroids are kind of stuck in these positions, about 60 degrees ahead or behind the planet Jupiter. Here's a look at this, Jupiter with the asteroid belt and the inner planets. Here's Mars here. And here is an animation showing cataloged asteroids, the asteroid belt. And we can see Jupiter over here with these two blue groups here signifying the Trojan asteroids. So about 60 degrees behind and ahead of the planet Jupiter as we look at these very active inner solar system here. Here are some properties of asteroids. About 75% of them are carbonaceous, which means they're comprised of carbon, which happens to be a major building block for, as we know it, for life. 15% are silicate, which means they're made of rock, silicon dioxide. And 10% are metallic, which means they're made of pure metallic type rock. Carbon is rock as well, could be rock as well. Origin of asteroids. Possibly the asteroids were fragments of a planet that broke up long ago. If you believe in the Titus-Bode law, the empirical law, which really should have no true scientific significance maybe, then you would say that where the asteroid belt is, there should be a planet. And so that planet just broke up and formed the asteroid belt. Or possibly there are fragments that should have formed a planet and somehow they didn't coagulate. They did not accrete into the planet like the other locations did, and hence you ended up with just all these fragments that never quite went through the process of accretion. So one way to visualize a planet, a thing in their neighborhood, to form themselves, unfortunately where the asteroid belt is, that didn't happen, and so no planet was formed there, and just all the material just was kind of left there. Too little mass in the asteroid belt to constitute a planet, so this last theory is probably the better one, that all this material just kind of was left there and never quite formed a planet. And as you look at asteroids, particular asteroids are a far different composition from each other, so it supports the idea that these pieces just never had a chance to coagulate into a planet and hence have a common composition. That concludes this first lecture on the solar system with general properties of the solar system, Chapter 4.